Section 5.3, Compound Interest. So in this section, we want to be able to solve problems involving compound interest. And getting into this, we saw simple interest in the last one. Simple interest is useful for some types of loans and investment situations, but the most common type of interest is compound interest. Credit cards, bank loans, home loans, savings accounts, mutual funds, your student loans, etc., all use compound interest concepts to determine the interest accrued, how much interest you need to pay. So your goal as a borrower should always try to get the lowest rate for the shortest time. And as an investor, you want the highest rate possible. That's what you're looking for. So recall, simple interest involved interest earned or paid only on the principal. So that initial investment is all that the interest was gaining on. So if you look at the formula here, the F equals P times parentheses 1 plus RT, close those parentheses. If you distribute that principal in, or the initial amount, you get P plus PRT. So this right here, this is the interest, the I, and it's only happening with the principal. There's no other interest coming in and earning more interest. So the compound interest will accrue interest on the principal just like simple interest does. And the interest. So this is what makes compound interest a much better thing for anyone who's investing, and maybe not so good a thing for people who are borrowing, because you're paying interest not only on the principal, but on interest that's accrued. So how does it work? Well, let's consider the following. Let's assume that you have $100 and your rate is going to be 0.1, so 10%. So when you start out, you put $100 in. At the end of the year one, or at the end of 1 year, more importantly, you will have 100 plus 100 times 0.1. Your initial plus the interest. And then this will equal 100 times 1 plus 0.1, and that will give you $110. So if you compared this back to what we did in simple interest at this point, after a year of interest being accrued on that $100 investment, you don't notice any difference. But if we go now to year two, after 2 years of interest, that 110 comes down now, and then you add that to, and this is where compound differs, you have 110 times 0.1 instead of 100. This is where the big change happens between simple interest and compound interest, because in simple interest, you just had 100 times that 0.1 every time. Well, now that extra $10 you earned in the first year, it's gaining interest during that second year. So this will then become 110 times 1 plus 0.1. And if we just take this amount right here and replace that 110 with it, what you're seeing here, I hope, is something to what I did similarly with the exponential growth. And, as we saw with the simple interest, it was linear. And what I want you to understand now is we're starting to see that this compound interest is not linear. It's in fact going to be exponential. So just moving some things around here, I'm going to write this as a square. So we see that power coming in just like we did with the exponential stuff. And this will now equal $121. So if you compare this back to the simple interest, you actually earn an extra $1 because you earn 10% on that $10 that you earned during that first year of accrual. So, you're earning interest on the interest. That's the key aspect of compound interest. So then I'll bring this 121 down here, and then we'll take 121 times 0.1. So we're earning interest on everything that we've earned up to this point, including the initial investment. And then we'll have 121 times 1 plus 0.1. And again, I'm going to rewrite that 121 as 100 times 1 plus 0.1 squared. So basically taking this here and replacing the 121 with it. And then we multiply that by the extra 1 plus 0.1. And when you work this out, you get 100 times 1 plus 0.1 cubed. So you're seeing that power, just like we did in the exponential growth, matching the number of years that this money has been allowed to gain interest. So the total amount after 3 years of accrual will be $133.10. So we're gaining a little bit more every time. And let's go ahead and see a graph of this in Desmos. I'll compare it to the simple so that you can see what it looks like. Okay, so in this graph, I have in the red graph the simple interest, linear growth, and then in the blue graph, you have the compound interest. So they both start at that $100, and then after the first year, they both had 110. But after that, notice how that exponential curve happens for your compound interest. So your compound interest just starts blowing away the amount of money you can earn in simple, because you keep earning interest on the interest you've already earned, and it just keeps steamrolling and snowballing and becoming this much bigger amount. And you can see it as time goes on, it gets even more and more different than if you were just to stay with simple interest. You gain even more and more and more. So that exponential growth is a characteristic of compound interest. So going back over the notes here, the general formula for compound interest does have that exponential element to it. We can see this NT power. So you have the future value still as F, present value still as P, or principal. You can think of that as your starting amount, the principal. And then you have 1 plus r over n, and then to the nt power. So this r over n, you might be wondering why r over n. And the r is still your annual percentage rate changed to a decimal. That doesn't change. T over in the power is still number of years, but this new n, this is the number of compounding periods per year. So, you might be compounding monthly, daily, quarterly, weekly, and when you compound like that, the annual rate that they quote, you're not going to get paid, let's say we're 10%, for the annual, you're not going to get paid 10% every month. That's not how it works. So this R over N is really the periodic rate. So they divide it by the number of compoundings per year in order to get the actual rate per month, or maybe the rate per week or per quarter. So that's why they divide that by N in order to adjust the yearly rate to be a periodic rate. And then the NT up here in the power, since you might be compounding more times than just once per year, you will actually have to consider the n times the t as the total number of compoundings over the time. So it's just the total number of compoundings. So if you're going 12 times a year, monthly, and you're going 10 years, then you've actually compounded 120 times, 12 times 10. So the total number of compoundings is more important for the compound interest than just having the years. So that's why they got that n in play in those two places. You adjust the rate to just be smaller depending on how many times you're compounding per year, and then you have to figure out the total number of compoundings to get the right answer in the end. So there will be some keywords associated with that n. And I missed one in here when I was putting this together, but it's not too bad. So you have the weekly as well. But basically, if you see annually or yearly, sometimes the homework will say yearly, n is going to be 1. If it's semi-annually, n is 2. If it's quarterly, n is 4. Monthly, it's 12. Daily is 365. Weekly is 52 weeks in a year. Now, this last one here, or I should say second to last, with the daily, the Banker's Rule, which this book does not use, but if you ever see a Banker's Rule in another class, n equals 360. And I've seen different reasons for why that is. I think the actual reason is it was easier to work with 360 than it was to work with 365 back in the days before calculators were a big thing. So that seems more reasonable to me. The other one I've heard is, there's 5 major holidays or whatever, and they just decided not to count those. But I don't think that's really the truth. I think it's, from some of the things I've looked into, it was easier to work with. So at any rate, if you see these keywords, you're going to be using n equal to these numbers. And Banker's Rule, again, this is not in our book. So if you do see that, though, you'll use 360 instead of 365 for daily. All right, so let's see here. I think we have enough time for an example in this video. So let's see an example here. Maisie invested $5,000 into an account, paying 7.6% compounded yearly. How much money will she have in 3 years? So one of the biggest things that you have to do with these types of problems in Chapter 5, now that we're starting to get into the formulas, we had simple interest, we have compound interest, we're going to see other formulas in the following sections. You really have to identify first what formula you're using, and then you have to be able to identify all the pieces that you have in order to fill in the formula so you know what you have to solve for. So the first thing that I see here, as I'm reading through there, as soon as you see compounded yearly, compounded some amount of time, you're going to be using the compound interest formula. So F will equal, just go ahead and write it down, get it down here so you know what you're working with. So as soon as you see that compounded, and then maybe monthly, yearly, whatever, write down that formula. So then we go back in here and I'm going to see what information I have. Invested $5,000. Well, that's the principal right there, or the present value. Paying 7.6%. You always assume APR here. So this is our R. We need to adjust that to be a decimal. So 0.076. Yearly. That's a key word now that we're compounding, but yearly just means n equals 1. And then how much will she have in 3 years? So this is going to be the T right there, that 3. So then you just plug all these pieces of information in. You plug the 5,000 in. 1 plus 0.076 divided by 1, just to make it clear that we are dividing by the n, and then raised to the 1 times 3 power. And in Desmos, I would recommend you put parentheses. Lots of parentheses here. If you're lazy on parentheses, you may get the wrong answers. So make sure you're just using parentheses like crazy with these financial formulas, because calculators especially get a little crazy with them. But if we work this out in the calculator or in Desmos, you get $6,228.83. So got a little bit of time here. I'm going to go ahead and show this in Desmos. So let's go right over there and just type this in. So 5,000 times 1 plus 0.076 divided by 1. Right arrow to get out of there. Shift 6 to get to the power. And then parenthesis 3 times 1. So what you're looking at there then, that's the answer. So it should look something like this when you type it in the Desmos. And then you can just adjust different values with these problems in the homework in order to get new answers.